In this lecture, we will continue our discussion on the linear representations or groups. We will begin with a discussion of a special kind of representation which will turn out in the end to be quite general. These are called unitary representations. We will then go on to describe a procedure for creating larger representations out of smaller ones, the so-called direct sum of representations. This discussion will automatically lead us to the concept of reducibility of representations, a concept which will turn out to be of immense importance for physical applications. Let us begin with a discussion on unitary representations. A unitary representation of a group is one in which every group element is mapped onto a linear unitary operator. Of course, because it's a representation, this map has to obey the standard requirement that L of G1, G2 is LG1 times LG2. But on top of that, each of these operators have to be unitary. Now, as it turns out, unitary representations are very, very important, both for theoretical reasons in the development of the theory of group representation, as well as for practical reasons, including applications to physics. Now, one of the reasons why a unitary representation is so useful is that it makes many calculations a lot easier, as you will see as the course unfolds. And another reason, one which is going to be proved to you quite soon, is that every representation for a finite group is equivalent to a unitary representation. So even if a given representation is not unitary in itself, it can always be changed by a similarity transformation to a unitary representation. By the way, this result actually can be extended to a special class of infinite groups as well, called compact groups. We are going to discuss compact groups later on in the course. Let me just say this much. Compact groups are also very important in mathematical physics as well as for direct physical applications, basically because compact groups also allow unitary representations. So exactly what is a unitary representation? As I said, a unitary representation is one in which every operator corresponding to a group element is a unitary operator. So let us first recall what the definition of a unitary operator is. To do that, let me first define what an adjoint of an operator is meant to be on an arbitrary inner product space. So given a linear operator T, which is a map from capital V to capital V on an inner product space V, we can define the adjoint of T by the following relation. For all vectors small v1 and small v2 belonging to capital V, the inner product between v1 and t v2 has to be equal to the inner product of some operator acting on v1 with v2, and this new operator, the one which acts on v1, the first factor in the inner product, is called the adjoint operator. T dagger adjoint to T. Of course, you have all learned about this in quantum mechanics. This is just the more general version which is available for all inner product spaces. You should actually confirm that your idea about what an adjoint operator is from quantum mechanics is consistent with this definition. As it should be. After all, the quantum mechanical adjoint operator is a special case of this more general definition. Now, operator U is said to be unitary if it obeys this particular relationship, which simply says the operator's inverse is its adjoint. Of course, it first says that the operator is invertible and then claims that its inverse is nothing other than its adjoint. And a unitary representation L of a group G on an inner product space V. So this is very important. You cannot talk of a unitary representation unless you are on an inner product space, is a representation in which for every element small g of capital G, the operators LG are unitary. This is something I have already said, but since we have now defined formally what a unitary operator is, what we are really claiming is for all small g belonging to capital G, LG dagger LG is the same as LG LG dagger and is the same as the identity. In other words, for each of the LG dagger is the same as LG's inverse. Note that while we have chosen to state this definition in the language of linear representations, so we are talking of unitary operator representations, we could have just as well talked about unitary matrix representations. And there, of course, every matrix representing a group element would have to be a unitary matrix. And recall that a unitary matrix is a matrix which is invertible and its inverse is equal to its Hermitian adjoint. In other words, its inverse is the same as what you would get if you were to transpose it and then do complex conjugation on it. In fact, some of the results that I am going to quote, in fact the very next result that I am going to quote, may be easier for you to follow in the language of matrix representations. I am going to state it in the language of linear operators, but it will be very easy for you to translate that in the language of matrix representations and understand it using that language if that is what you are more comfortable with. Both are equally useful and they are basically two different ways of saying the same thing. So let me turn now to the all-important result about unitary representations that I have already referred to before. Every representation L of a finite group capital G, note the stress on the word finite, on an inner product space capital V is equivalent to a unitary representation on the same vector space. So this is a theorem and this is what we are going to prove now. Note that this is the theorem which makes unitary representations so important. So for the proof, what we do is we start with any linear representation of the group small g, this L, and form an operator by doing this particular thing, which is I am going to take the product of the two operators LG dagger LG and then I am going to sum this over the entire group. This summation over all the group elements is perfectly well defined because we are dealing with finite groups. For infinite groups, some of the steps that we are going to carry out in this proof may not be legitimate ones, and that is precisely why we have stated this result for only finite groups. As we also hinted at the beginning, these results can be extended to compact groups, but that is specifically because some of those steps where there could be a problem in handling infinite sums can be handled specifically for compact groups. Once again, we are not really talking about compact groups now, so let us stick to finite groups. This is just a finite sum of a bunch of operators. But this summation over all elements of a group is actually a very important technique which we are going to use over and over again during the course of these lectures. And you will see that many important results in group representation theory can be figured out using this particular technique. So, apart from the inherent importance of this particular result, the technique that I am going to use here is very, very important for the rest of the course. So, it's important that you understand this technique thoroughly. Now, each of the terms in this sum are Hermitian and positive definite, which means that the sum x is a Hermitian and positive definite operator. Now, it's a very standard property which we learn about in linear algebra that any Hermitian positive definite operator has a spectral decomposition of this following form. It can be always written as a sum over some eigenvalues lambda of lambda times p lambda, where all the lambdas are necessarily positive and the operators p lambda are actual projection operators. That is, they obey the property p lambda prime delta lambda prime lambda times p lambda. So basically what we are saying is that the operator can be thought of as made out of projection operators which project to its different eigenspaces. Now the all important thing here is that lambdas are positive. As a result, they have a unique positive square root of lambda, and they are all well defined. So we can use that to define a new operator S, which is root over lambda times p lambda. Now, using the fact that the p lambda are projection operators, it's very easy to verify that if you were to square the operator s, that is multiplied by itself, you are going to get x. So this s is a Hermitian positive definite operator and squares to x. As you will soon see, it is this operator s which is the one which will be used to carry out the similarity transformation, which will change the representation to a unitary one. To see how this comes about, let us consider the following. Let us multiply the operator x by LG dagger on the left and LG on the right for a particular LG. That is, this is for a specific small g belonging to capital G. And of course, x is the same as s square. So this is really L dagger G S square LG. Now, use the fact that x is a sum over the entire group, which is of course LG prime dagger LG prime with G prime running over the entire group capital G. G is a specific group element here, which is why the summation index has to be changed to G prime. But now what you can always do is you can bring in the LG dagger from the left inside the sum and bring the LG from the right inside the sum. And that will give you LG dagger LG prime dagger times LG prime LG. But note that LG dagger LG prime dagger is actually LG prime LG's dagger. So this sum really is a sum as G prime runs over the entire group capital G of this quantity LG prime LG's dagger times itself. So this has exactly the same form as a sum which defined capital X, except that in capital X we had LG prime dagger LG prime. Here what we have is actually L of G prime G dagger L of G prime G. Here of course what we have used is the fact that LG is a representation and hence is a homomorphism. Now comes the most important part of the proof. As G prime runs over the finite group capital G, the G prime G, the argument which is being provided to L here, also runs over the entire group capital G. For a finite group, this is just the rearrangement theorem. And what that implies is that the terms in this sum are exactly the same as the terms that were there in this sum, except that they have been rearranged in some other order. But because this is a finite sum, the rearrangement does not change anything, and so this thing really is the same as x. Of course, x is s square, so this is the same as s square. So the upshot of all this is L dagger G s square LG is s square. But what we will then do is simply multiply this expression both on the left and on the right by S inverse to end up with this result. S inverse L dagger G S times S L G S inverse is the identity. Here the curly I stands for the identity operator on the vector space V. Note that because S is a Hermitian operator, S inverse LG dagger S is the Hermitian adjoint of S LG S inverse. As a result, if I were to define a set of similar transformations, similar to LG I mean, for each G, by L prime G equals S LG S inverse, then each of the L prime G's for each and every small g will obey L prime G dagger L prime G equals the identity. What that means is that the L prime G operators are unitary operators, and because they are similar to the original LGs, what you have is that L prime will define a unitary representation which is equivalent to the representation L. So this concludes our proof that for a finite group, each and every representation is equivalent to a unitary representation. Now this proof may seem a bit abstract to you at this stage, so let us just take a look at a particular specific example to understand exactly what is being done. Now, For the example, what we will do, fall back on our old friend, the group S3, the group of symmetries of an equilateral triangle. And we have already seen a couple of representations for that group. We have seen the two-dimensional representation and also a three-dimensional representation furnished by the action of the group on the space of homogeneous quadratic functions. Now, as it turns out, the representation that we actually obtained on the two-dimensional vector space R2 is already a unitary representation. This is something you should check for yourself, that all the 6 2x2 matrices that we had obtained there are unitary matrices. So, in order to illustrate the steps in this proof, what we are going to do is we are going to take a look at the 3x3 representation that we had obtained later, and that 3x3 representation happens to be non-unitary to begin with. Just to remind you, these were the 6 matrices we had obtained by the action of the group on the function space of homogeneous quadratic functions, where we had chosen the basis comprised of the functions, the 3 functions, which mapped a vector x comma y to x square, y square and xy respectively. And as you can easily check, these matrices are not unitary, at least not all of them are. Obviously, the identity matrix is unitary, so is the matrix for matrix dA, the representative for the A reflection, but the other matrices actually are non-unitary in this case. Now, in order to carry out the procedure, what we will do is we will form the matrix, in this case, dE dagger dE plus dA dagger dA and so on up to dF dagger dF. And if you carry out the calculation, I'm not going to bore you with the details of the calculation here, but if you carry out the calculation, what you get is this matrix. X, which is 15 by 2, minus 3 by 2, minus 3 by 2, 15 by 2, 9 by 2. So this happens to be a Hermitian matrix. Of course, this being real, Hermitian simply means symmetric, and that's sort of obvious. It is also positive definite, and in order to understand whether that is correct, what you need to do is look at the eigenvalues of this particular matrix, and the eigenvalues all will turn out to be positive. And using the eigenvalue-eigenvector decomposition, I can diagonalize this matrix, take the square root of the diagonal matrix that we had obtained, and then invert back to come back to the square root of x. This is a pretty standard procedure in linear algebra. I'm pretty sure all of you can carry that out. And this will give rise to this particular matrix S, which is the square root of x. You should be able to carry out this calculation yourself. Check that if you were to calculate the square root of S by diagonalizing x first, taking the square root and then inverse diagonalizing or inverting the diagonalization, you do get this particular matrix S. And after this, what I'm going to ask you to do is carry out the symmetric transformation induced by S on each one of these 6 matrices and check for yourself that the resulting 6 matrices turn out to be unitary. I will leave the details of this as an assignment for you. But this is something you should be able to do explicitly and convince yourselves that the steps that I outlined in the proof not only give you a proof that every representation of a finite group has an equivalent unitary representation, it also gives you a perfectly good procedure for finding that equivalent unitary representation. As I have said time and again, the fact that a finite group has representations which, if not unitary themselves, are always equivalent to a unitary representation happens to be very, very useful. Sometimes the utility is because it is easier to deal with unitary representation. Some calculations become a lot easier. However, sometimes you don't even need the representation that you're using to be unitary. The very fact that it is equivalent to some unitary representation is enough for you to prove some very interesting results. as you will see when we talk about the orthogonality of the character vectors, which is a very important result in this course. But all that is for later. Now we are going to talk about a different kind of representation, a kind of representation which you can build up out of smaller representations. That is, we are going to talk about direct sum of representations and in the process talk formally about reducible and irreducible representations. I know I have mentioned these things in passing several times during this course, but we have never really formally defined what a reducible representation is. That is what we are going to do soon in this part of the lecture. As is the case for most results in representation theory, this concept of direct sum of representations can be expressed in both the matrix language and the operator language, and it will turn out that each version has its own advantages as far as familiarity or ease of use is concerned. So what we will do is we will talk about these concepts in both languages. We will begin with the one which is more familiar to all of you, I guess, the matrix language. And here what we do is we start with the idea that we have two representations of dimensions n1 and n2 respectively. These are both matrix representations, and these matrix representations are going to be called d1 and d2 respectively. Note the 1 and 2 on top is being written in brackets, of indicating that these are of course not powers. These are just labels which tell you that these are two different representations. Of course, when you say that these are representations of group capital G, you mean that these are maps which associate with every group element small g of capital G, a n1 by n1 matrix and a n2 by n2 matrix respectively. So d1g for all of the g's are n1 by n1 matrices and d2g are n2 by n2 matrices. Now consider a big matrix of dimension n1 plus n2 by n1 plus n2 for a given small g defined in the following manner. Capital D of G is defined to be a matrix which can be written in this block form, where the first n1 rows and n1 columns are occupied by d1g. This is n1 plus n2 dimensional square matrix. So that means that there are still n2 more columns to be filled up here of the first n1 rows, and those entries are all 0. Similarly, there are n2 rows which are still left after you have placed the d1g up here, and those n2 rows of the first n1 columns are all filled with zeros. So what you have are two rectangular matrices, sub-matrices inside this big matrix. One is n1 by n2 dimensional null matrix, the other is an n2 by n1 dimensional null matrix. And that leaves a corner with n2 by n2 elements left, and that is occupied by d2g. So for every small g there is a d1g matrix and there is a d2g matrix. You put them along the upper corner and the lower corner of an n1 plus n2 by n1 plus n2 matrix, and then you fill up the rest of the portions by zeros. This is how you produce your capital D of G. Now my claim is that this procedure of creating a big n1 plus n2 by n1 plus n2 matrix for every small g will give rise to a representation, a matrix representation of dimension n1 plus n2 for the same group capital G. And in order to check that, what we need to do is check what happens when you take d of g1 and d of g2 and multiply them together. If this is a representation, what you should get is d of g1, g2. Now, I'm pretty sure all of you know how to handle blocked matrices. If you have two matrices which are blocked in this manner, when you multiply them together, you can actually pretend that every one of these blocks are actually elements of a 2 by 2 matrix, and just use the standard rule for multiplying 2 by 2 matrices. So, when you multiply these two matrices, you will get d1 g1 times d1 g2 plus 0 times 0. You should check that this 0 of course is n1 by n2 and this 0 here is n2 by n1. So their multiplication is actually well defined. An n1 by n2 matrix multiplied by an n2 by n1 matrix actually gives you a perfectly good, legitimate product. So that an n1 by n1 null matrix which you can add to d1, g1, d1, g2. So these operations are well defined. Although you're not adding numbers here or multiplying numbers and adding them together, you should actually convince yourselves that each one of them, when you were to treat each of these matrices as if they were numbers, gives rise to legitimate matrix manipulations. There is no problem with the row column number and anything like that. If you carry out this calculation, it's pretty simple to end up with the answer. The answer is d1, g1, d1, g2. In this corner will be 0. This corner will also stay a null matrix. Of course, 0 here means a null matrix. And this corner will have d2, g1, d2, g2. Now remember, d1 and d2 are both representations. And what that means is d1, g1 times d1, g2. This matrix multiplication is actually d1 of g1, g2. And this corner here is d2 of g1, g2. So when you multiply them together, you end up with this result. D of g1, d of g2 is a block diagonal matrix of this kind, with the blocks having elements d1, g1, g2 and d2, g1, g2 in the two corners. And if you just go by the standard rule that we have been using, this is of course d of g1, g2, which is exactly what we have been trying to prove. Thus what we have achieved is that out of two representations of dimensions n1 and n2 respectively, we have created a bigger representation of dimension n1 plus n2. Now from the block diagonal form which each of the representation matrices are in, it is obvious that you have created this big representation out of the smaller representations. However, if after doing this, I had changed the basis in the underlying vector space, or in matrix language carried out a single similarity transformation by the same transforming matrix on each and every one of these group representation matrices, then the rows and columns would have gotten mixed together and this block diagonal structure would no longer be apparent. It would still be there and would be revealed if I did the inverse similarity transformation back on every one of the matrices. However, if you just took a look at them, this structure may not be obvious. Now, if such a structure exists, that is, if all the matrices in the representation are either already in a block diagonal form or can be recast in a block diagonal form with exactly the same block diagonal structure, by doing a given similarity transformation on all of them, then we call this representation reducible. We are simply acknowledging that this representation had really been built out of two smaller representations, two or more smaller representations. If this cannot be done, then you say that the representation is irreducible. In other words, a matrix representation is irreducible if no similarity transformation exists such that if you were to carry it out on each and every one of the representation matrices, they will all acquire a block diagonal form with the same block diagonal structure. Now you must realize that it's very difficult to prove that something does not exist in general. If you can find a similarity transformation which makes all the matrices block diagonal, then you have actually managed to show that your representation is reducible. However, if you cannot find any such transformation, that might be a sign that such a similar transformation does not exist. It might also be a sign that you simply not searched hard enough. And usually what will happen in a physical application or in a mathematical application is that you will create a representation from some other considerations, like use the standard methods of the function space representation to find a large representation. And the form in which this representation appears in front of you may not make it obvious that it is reducible. That is, it does not come in an already block diagonal form. This task that you have of trying to figure out whether it is reducible or not then becomes a rather difficult one. If you can find a similar transformation which makes all of the matrices block diagonal, fine. If you can't, then you are in trouble because you do not know whether your inability to find such a similarity transformation is because there is no such similarity transformation in the first place, in which case, of course, the representation is irreducible, or whether it is simply because you have not tried hard enough. Thankfully, there are results in group representation theory, which we will discuss over the next few lectures, which will make it easy for us to judge algorithmically, given a matrix representation, is it reducible or not? And not only that, also tell you exactly what smaller representations it is made up of, and in fact, with a bit more effort, also tell you exactly what kind of change of basis or similarity transformation to carry out so that this reduction will be obvious to everybody. This happens to be very, very important for physical applications because, as we have hinted several times before, in most physical applications, the irreducible pieces of which a given representation is built out of has immense physical significance. And that, of course, is the reason why we are spending so much time discussing the notion of reducibility. We will continue with our discussion of reducibility, but this time, instead of using matrix representations, we are going to talk about reducibility in the language of operator representations or linear representations. In order to understand this, we need to first recall a concept from linear algebra, that of the direct sum of two vector spaces. So we start with two vector spaces v1 and v2. Once again, the 1 and 2 has been written here as suffixes. They are within brackets, just so that you do not confuse them with powers. Now the direct sum of these two vector spaces is defined in terms of two things: the underlying set of elements, our vectors, and the law which we use to combine those vectors. Just as in group theory, we have a basic notion of a product of two elements. As you all know, in linear vector spaces, the basic notion is actually twofold. You need to be able to add two vectors. You also need to be able to multiply vectors by scalars. Or, put together, you need to be able to linearly combine two vectors with scalar coefficients. So, the underlying set that we are talking about here is basically nothing but the Cartesian product v1 times v2, which of course is a set of pairs small v1 comma small v2, where small v1 comes from the vector space capital V1 and small v2 comes from the vector space capital V2. As I said, just specifying the set is not enough. What we need to do is specify the combination rule. And the way in which we linearly combine two vectors, v1 comma v2, the pair, with the pair v1 prime, v2 prime, with coefficients alpha and alpha prime taken from the scalars, is simply we form alpha v1 plus alpha prime v1 prime, which of course is a genuine vector in capital V1, and the vector alpha v2 plus alpha prime v2 prime in capital V2, and put them together in a pair. So this is how you define the direct sum vector space v1 O plus v2 of the vector spaces v1 and v2. You should of course check that with this combination rule, all the basic properties of a linear vector space are actually satisfied by v1 O plus v2, but that is really a rather simple thing to check. Now, as you have seen before in the case of direct product of groups, this is also a situation where each vector space does its own thing. That is, you essentially combine vectors of v1 with each other and vectors of v2 with each other, and they don't interfere among themselves at all. Now, given this independence, so to speak, of the two constituent vectors which make up an element of the direct sum vector space, it is sort of easy to see how you can define a representation on the direct sum space if you have two representations L1 and L2 on the two vector spaces V1 and V2 of course, the same group, capital G. How you define this representation is as follows. You define the direct sum representation L1 O plus L2 of G by specifying that what LG does to a vector V, which of course comes in form of a pair, one vector from capital V1, another vector from capital V2, namely small v1, small v2. What LG does on V is that it returns a pair of vectors. The first entry of that pair is what L1G does to V1, and the second entry is what L2G does on V2. So notice that this is where both at the level of the way in which the vectors combine and the way in which the operators act on the individual vectors, we have independence among the two vector spaces. Basically, each vector space is doing its own thing. This should be very reminiscent of the way in which we define direct product of two groups, and essentially is the same structure. However, let me warn you about one potential confusion which may arise later. We are going to talk about direct product of representations in a later lecture, and that's going to be very important for us as another means of building up a big representation out of smaller representations. However, that direct product representation is pretty different from this. So it is actually the direct sum of representations which is more analogous to direct product of groups. The direct product of representations is slightly more complicated, if you can call it that. So just to emphasize, direct product of groups essentially is similar to direct sum of group representations. There are of course different things. One is a way of building bigger groups out of smaller ones, and this is a way of building bigger representations of a given group out of smaller ones. But to repeat, they are similar in the sense that just as in a direct product group, individual group elements work among themselves, here individual vectors combine among themselves and individual representations act on their individual vector counterparts. This then is the direct sum of two representations in the language of operator representations, that is, linear transformation based representations. What exactly is the connection between this and the matrix representation language version of the direct sum? In particular, what is the connection between this and the block diagonal structure that we saw matrix representations would have? The answer lies, of course, in choosing a basis in the direct sum vector space. And given bases on the two individual vector spaces, there is an obvious choice of basis for the direct sum space. If ei1, that is I running from 1, 2, 3, 4 up to n1, and ej2, j running from 1, 2, 3 up to n2, form bases of v1 and v2 respectively, then a natural choice of basis for v1 direct sum with v2 are the vectors of the form where, of course, being vectors of v1 direct sum v2, they have to be pairs, the first vector coming from capital V1 and the second one coming from capital V2. We choose vectors which have the basis vectors of the first vector space V1, ei1 as a first element, and the null vector of V2 as a second element. That's one set of n1 vectors. Another set of n2 vectors come in when we put the zero vector from V1 as the first component of a pair and the basis vectors of V2 as a second component. This gives us n1 plus n2 vectors in total, and these obviously form a basis of the vector space V1 direct sum with V2. Now that we have an order set of n1 plus n2 vectors which form a basis of the direct sum vector space V1O plus V2, we are in a position to talk about what the matrix representation corresponding to the direct sum representation of two representations L1 and L2 on V1 and V2 respectively look like with this particular choice of basis. Note that of these n1 plus n2 basis vectors, the first n1 are effectively basis vectors of V1 and the last n2 are basis vectors effectively of V2. However, they have been written in such a form that they actually are vectors of the direct sum space V1 O plus V2. Now, when the operator L of G where L is the direct sum of the two representations L1 and L2 acting on V1 and V2 respectively, acts on any one of the first n1 basis vectors, that is, the basis vectors of the form ei1, 0, then the action is simply L1g acting on ei1, L2g acting on 0, where 0 of course is the null vector of V2. Since the null vector of V2 under the action of a linear operator returns a null vector, of course what you get is simply L1g ei1, 0. Now, since L1g is a representation of the group G on V1, it must have an equivalent matrix representation D1 of G. So we can use the connection between D1 and L1 to simply write the first components in the form of this sum. So the action of L of G on ei1, 0 simply becomes sum from k equal to 1 to n1 dki1g ek1, 0. Of course, this means that when LG goes and acts on the first n1 basis vectors, the resulting vector can be expanded in terms of only the first n1 basis vectors. The other n2 basis vectors do not appear in this expression. So when we write down the corresponding matrix for the direct sum L of G, then what will happen is for the first n1 columns, the column is of course labeled by ei1, we will get the elements from D1 on the first n1 rows, and the n2 rows which come below that will all have 0 entries. Similarly, LG acting on 0, ej2 will just return 0, L2g acting on ej2, and thus can be expanded in a sum from L equals 1 to n2 of dlj2g 0, el2, and this means that for the last n2 columns of the matrix equivalent of LG, we will have zeros in the first n1 rows, and D2 elements will occupy the final n2 rows. As a result, the matrix representative of L of G will end up having this block diagonal structure. D1G will be sitting on the first n1 by n1 corner elements. D2G will be sitting on the n2 by n2 corner elements on the other side, and the rest of the elements will be filled with zeros. Thus, the matrix representation for L of G, when expressed in this obvious choice of basis for the direct sum vector space, will have the standard block diagonal form which we have seen in the case of direct sum of matrix representations. Now, in the case of matrix representations, we had stated that a matrix representation is reducible if it is either block diagonal or can be converted to a block diagonal form by some similarity transformation, the same similarity transformation acting on each and every one of the matrices. For an operator representation, the definition of reducibility is slightly easier. An operator representation is called reducible simply if it is a direct sum of two or more representations. Of course, the moment it is a direct sum of two or more representations, it stands to reason that the corresponding matrix representation will also be of the block diagonal form if you happen to choose your basis in this particular manner. While this particular definition of reducibility of a linear operator representation is perfectly mathematically legitimate, an alternate way of stating the same definition might prove more convenient for applications. And to realize that, let us first consider two subsets of the direct sum space V1 and V2. In the first set, we consider pairs. Remember, all elements of V1 O plus V2 are actually pairs, where the first vector comes from capital V1 and the second vector comes from capital V2. The particular subset we are considering first is one in which the first vector is an arbitrary vector from capital V1 while the second vector is just the null vector of capital V2. Similarly, the second subset that we are considering is the one in which the first vector happens to be the null vector of capital V1 and the second vector is an arbitrary vector of capital V2. The connection between these two subsets and the basis that we talked about, the special basis that we talked about a while ago, should be rather obvious. In fact, both these subsets happen to be vector spaces in their own right, and these vector spaces are spanned by the two sets of basis vectors, the first n1 and the second set of n2 vectors that we talked about just now. And these subsets are of course isomorphic to capital V1 and capital V2. Isomorphic here of course is being used in the linear algebra sense of isomorphism between linear vector spaces, not isomorphism between groups. This is a very similar concept. Two vector spaces are considered to be isomorphic if there is a one-to-one invertible mapping between them, which preserves the basic important structure in linear vector spaces, namely linearity. Now, if you take LG and make it act on any vector from the first set, that is any vector of the form v1, 0, of course you are going to get L1G v1 and 0 for the second vector, second part of the pair. Similarly, LG acting on 0, v2 will give you 0, L2G acting on v2. Hence, the first set, the set of all vectors in which the second part of the pair is a null vector of v2, is invariant under the action of LG. If you apply LG on every one of these vectors, you get only a vector in that set. Similarly, the second set of vectors, the subspace isomorphic to capital V2, is actually invariant under L of G. This helps us to give an alternative characterization of reducibility of a representation. In this alternative characterization, we start from an arbitrary vector space V on which some representation L of a group capital G is given. We claim that the operator representation L on a vector space capital V is said to be reducible if there exists a subspace V prime of V which is invariant under the action of L of G for all small g belonging to capital G. Note that when we knew our vector space was a direct sum of two vector spaces V1 and V2, and we had a direct sum representation which was acting on this direct sum vector space, then the two vector spaces isomorphic to V1 and V2 were vector spaces which had this property, namely they were subspaces of V1 O plus V2 which were both invariant under the action of LG for all small g belonging to capital G. Here we are demanding that if there exists a non-trivial subspace V prime of V which is invariant under the action of LG for all small g belonging to capital G, then the original operator representation L on capital V is reducible. Now, is this definition of reducibility that we have stated right now the same as the definition that we gave a while ago? Well, yes and no. For all practical purposes, they are the same definition, especially if we are talking about finite groups. We will see why, partly in this lecture. Maybe we will carry over till the next lecture until we fully understand why these two notions are equivalent, especially if we are considering finite groups. But to see the connection between this particular definition of reducibility that we have introduced right now to the notion of the block diagonal form that a matrix equivalent will have, we will of course have to start with a basis on capital V. And here, since V prime, the subspace of V which is invariant under L of G for all small g belonging to capital G plays a special role, we will choose the basis keeping V prime in mind. We will consider an ordered basis E1 to E2 up to En prime of V prime, which is extended to a basis of capital V. That is, you add enough linearly independent vectors to the set E1, E2, E3 up to En prime and keep on extending the basis until you end up with a basis for all of capital V. This is a pretty standard procedure in linear algebra, and I'm pretty sure all of you know what this is really all about. Now, when you start with such a basis and apply L of G on the first M prime basis vectors, that is L of G acting on E1, E2, E3 up to En prime, what we get is a linear combination of E1, E2, E3 up to En prime only. This of course follows from the fact that V prime is invariant under L of G. An immediate consequence of this is that when we form the matrix elements for D of G, which is the matrix equivalent of L of G in this particular basis, for the first n prime columns, only the first n prime rows will have non-zero numbers. All the numbers below that in those columns will have to be 0. Here n double prime simply stands for the number n minus n prime of the other basis vectors. And since LG EI for EI running over E1 through En prime has no contribution from En prime plus 1, En prime plus 2 up to En, we are going to get zeros here. Now what about what happens when LG acts on En prime plus 1, En prime plus 2 and so on? Since we have made no statement about whether the space spanned by these basis vectors is actually invariant under the action of L of G or not, at this stage we cannot say anything much about them. The final n double prime columns of the n by n matrix could have non-zero elements all over the place. So, basically, the matrix representing D of G under this circumstance where capital V, the space carrying this representation, has an invariant subspace, and with this particular choice of basis where the first n prime basis vectors are actually basis vectors which span that invariant subspace, the matrix representation will end up being of this form, which is not block diagonal but rather block triangular. It so happens that these square matrices, the submatrices D1G and D2G of dimensionalities n prime and n double prime respectively, will actually be representations of the group themselves in their own right. You can easily check that the fact that D is a representation, hence D of G1 G2 is D of G1 times D of G2, will lead to D1 of G1 G2 being equal to D1 G1 times D1 G2, as well as D2 of G1 G2 being equal to D2 G1 times D2 G2. So, as I've said, both the square matrices along the diagonals of this block triangular form happen to form representations of their own. As we have seen, the presence of an invariant subspace does not immediately lead to a block diagonal form for the representation matrices. So when do we actually get to see a block diagonal form? This happens when V is a direct sum of two or more invariant subspaces. Notice that here we have only stated so far that V prime is an invariant subspace. We did not make any such statement about the subspace spanned by the other basis vectors. If on the other hand, V were a direct sum of two or more invariant subspace, not only was V prime invariant under all the LGs, so also was the space spanned by En prime plus 1, En prime plus 2 all the way up to En, then it stands to reason that not only will the lower block be filled with zeros, even the upper block will be filled with zeros, because vectors which span the other subspace, En prime plus 1, En prime plus 2, etc., will also only become linear combinations of themselves under the action of LGs. Now this is called complete reducibility, which is exactly what we have been talking about so far. Now this distinction between mere reducibility, which follows when you just have an invariant subspace, and complete reducibility, when the space V is actually a direct sum of two or more invariant subspaces, is actually a matter of academic interest as far as finite or compact groups are concerned. Because, as we will see in the next lecture, there is no distinction between reducibility and complete reducibility for finite or compact groups. And in order to prove that, what we will make use of is the theorem that we have established earlier in this lecture, which is for every finite group, every representation is equivalent to an unitary representation. But all that is for the next lecture. Bye for now.